Arithmetic series is the summation of terms in an arithmetic sequence. Learn its procedure here in Mathematics of Engineering. In number patterns, the word series means the summation of terms in a sequence. In notation, this is written with a plus sign between the terms. And in sigma notation, S sub n, or the summation of terms until the nth term, is shown with the sigma symbol with the rule, which is commonly in its general formula. The formula for arithmetic series is S sub n is equal to half of the number of terms multiplied by the summation of the initial and final terms. This is a short formula, although oftentimes a sub n is not identified. So we can derive another formula by using the explicit formula of a sub n, which is a sub 1 plus the common difference times the quantity of n minus 1. So if this is plugged in S sub n and simplified, we can have another formula for S sub n, which is n all over 2 multiplied by twice of the initial term plus the common difference d times the quantity of n minus 1. How do we work with the sigma notation? Say we are to evaluate S sub n of the rule 3n plus 1 from n equal to 1 until n equal to 5. Since S sub n is the summation of terms, we have to identify the 5 terms involved first. So at n equal to 1, a sub 1 is 3 times 1 plus 1 giving 4. At n equal to 2, the term is 3 times 2 plus 1, and that is 7. At n equal to 3, or 3 times 3 plus 1, the third term is computed as 10. At n equal to 4, 3 times 4 plus 1 is 13. And at n equal to 5, we get 3 times 5 plus 1, resulting to 16. So to take S sub n, we add the terms 4, 7, 10, 13, and 16, which is computed as 50. For the second interpretation, it is required to determine the number of terms of the sigma notation shown. Using the rule, we can find the initial terms starting with s equal to 1. So 22 minus 6 times 1 is 16. At s equal to 2, we compute the term as 22 minus 6 times 2, which gives 10. Then we use another to validate the common difference. So at s equal to 3, the term is 22 minus 6 times 3, which is 4. From these 3 terms, we can determine the common difference by taking 10 minus 16, which is negative 6. And this is validated when we also compute the difference of 4 minus 10, which is also negative 6. Knowing d, we can solve for n in the series. So by plugging the given, we find negative 3,404 is equal to n all over 2 multiplied by 2 times 16, plus negative 6 times n minus 1. Let's simplify the terms in parentheses. So we have negative 3,404 is equal to half of n times 32 minus 6n plus 6. Collect constants to have negative 3,404 is equal to n all over 2 times 38 minus 6n. So if n all over 2 is distributed, we get negative 3,404 is equal to 19n minus 3n squared. And after fixing the order of the terms, we end up with 3n squared minus 19n minus 3,404 is equal to 0. With such function, we can use the quadratic formula to solve for n, and we get n equal to 37 and n equal to negative 92 all over 3. And since n is the number of terms, a fraction for an answer is disregarded, so the answer for the problem is 37. Next are some applications of the series formula. The first example is looking for the sum of the pattern with an initial term equal to negative 85 and the final term is 960 with n equal to 12. By using the formula, all we need to do is to plug all the given, making the formula S sub n is equal to 12 all over 2 multiplied by the quantity negative 85 plus 960. So by simplifying the numbers, we get S sub n equal to 5,250. Example 2 requires the summation of the first 22 terms of a sequence with d of 7 and a sub 22 as 149. With d and a sub n given, all we needed to find is the initial term before we can solve S sub n. So by the arithmetic sequence formula, we have a sub 22 is equal to a sub 1 plus d times 22 minus 1. We plug the values to get 149 is equal to a sub 1 plus 7 multiplied by 21, and we have the initial term as 2. At this point, all parameters are known from the formula, so we can start with S sub 22 is equal to 22 all over 2 times a sub 1 plus a sub 22. Provide the known variables to have S sub 22 equal to 11 times 2 plus 149, or that is 151. So the summation of the first 22 terms is 1,661. Example 3 states that when the third and seventh terms are added, it is equal to 6, but when multiplied, it is equal to 8. We are to look for the summation of the first 20 terms of the sequence. To find common variables with the given terms, we use the explicit formula for both a sub 3 and a sub 7. For the third term, a sub 3 is equal to a sub 1 plus d multiplied by 3 less 1. Simplifying the numbers in the parentheses, we get a sub 1 plus 2 times 2, or simply a sub 1 plus 2d. The seven terms process similarly as a sub 1 plus d times 7 minus 1. Then a sub 7 is equal to a sub 1 plus d times 6, or a sub 1 plus 6d. The first premise is a sub 3 plus a sub 7 is equal to 6. If we plug the expanded forms, we arrive at a sub 1 plus 2d plus a sub 1 plus 6d is equal to 6. Collect similar terms to get twice of a sub 1 plus 8d is equal to 6. And we can simplify the whole equation by dividing it by 2 to get a sub 1 plus 4d is equal to 3. We isolate a sub 1 as 3 minus 4d and consider this as the first equation. The second premise states that the product of a sub 3 and a sub 7 is 8. So using the expanded form, we get a sub 1 plus 2d multiplied by a sub 1 plus 6d is 8. This is the second equation. Having two equations for two unknowns, we can solve them simultaneously. So we continue by substituting equation 1 in equation 2 to get 3 minus 4d plus 2d multiplied by 3 minus 4d plus 6d is equal to 8. By simplifying the terms, we have 3 minus 2d times 3 plus 2d is equal to 8. Note that these two binomials are the expanded form of the difference of two squares. So we can place them together as 3 squared minus 2d squared is equal to 8. Or that can be simplified as 9 minus 4d squared is equal to 8. Collect all constants to get 4d squared is equal to 1. By now, we can take the square roots of each term and we get 2d is equal to 1. Thus, these solve as plus and minus 1/2. Having the value of d, we place this back to the first equation to get a sub 1 is equal to 3 minus 4 times plus or minus 1/2. By using positive 1/2, we get a sub 1 is equal to 3 minus 2, or that is 1. The other is a sub 1 is equal to 3 plus 2, and that is 5. Finally, we can find the required with the series formula. Starting with d as positive 1/2 and a sub 1 as positive 1, we can compute for s sub 20 as half of 20 times 2 times 1 plus half of 20 minus 1, or we simplify it as 10 times 2 plus half of 19, which is 10 times 11.5, and that is 115. Secondly, by using d as negative 1/2 and a sub 1 as 5, we can take s sub 20 as 20 all over 2 multiplied by 2 times 5 less half of 20 minus 1, or that is 10 times 10 minus half of 19, which is simplified as 10 times 1/2, or that is 5.